So as my colleague very nicely introduced already the plasticity part of the model, I want to continue, since this is the conference on fracture. We also want to address, of course, the topic of fracture. And overall, the whole motivation for this idea came from those series of experiments. Basically, to say a word to this picture. So a former colleague of ours, he exhibited those experiments on those thin-walled tubes. And under all those non-proportional loading types, we saw all different kinds of crack paths emanating. And our approach to address this phenomena here was then, as my colleague said already, to capture this within a phase field model approach. Now, as not all of you might be familiar with the phase field modeling, I want to give you a small introduction to the topic. So the point of departure, so to say, is the classical linear elastic fracture mechanics as it was originally proposed by Griffith. So in that scenario, we have a discrete crack path with discontinuity in the displacement field, and we have all within the bulk intact material states and the fully broken material state along this discrete crack paths. The basic idea of the phase field approach is now to essentially regularize this approach. That is, we want to smear this discrete crack over a certain width. This width is governed by a so-called length scale parameter. And to this end, to obtain such a formulation, we also need to introduce a so-called phase field variable, which now will take values in between 0 and 1. 0 denotes a completely intact material state. 1 denotes a completely broken material state. And within this regularized or smeared width, we now have a continuous increase of this phase field variable from 0 up to 1. Now, since I already stated that the starting point was linear elastic fracture mechanics, there's an obvious problem when we want to generalize this in order to capture a ductile fracture phenomenon, since obviously we are missing the information on the plastic deformation within this model. And it's really not straightforward to generalize this model. There are lots of approaches in the literature. And what came to our mind is to essentially make use of already known things. So for instance, continuum damage mechanics is known to offer a very convenient framework for exactly those type of phenomena. And if we have a look at gradient enhanced damage mechanics, we can realize that essentially the mathematical structure of phase field models and those enhanced damage, continuum damage models is essentially the same. So our aim of this talk, of the second part, is to essentially propose a phase field model, or to pick the best out of two worlds, a phase field model within the context of continuum damage mechanics. And yeah, this shall be done in a thermodynamically consistent manner. I have to admit this is a very, very interesting topic on its own, but due to the sake of time, I will not dive into this thermodynamically consistence within this talk. With that being said, the outline of the further talk is pretty much straightforward. I will first show some equations stating the main features of the proposed model, essentially a little bit recapitulating what my colleague said. And then I will show some pictures with some insight on the behavior of our material model. And in the end, of course, we have a conclusion and an outlook. Now, we're dealing with small deformations. We have, again, an additive decomposition of the strain into an elastic and plastic part. And we have also an additive decomposition of the energy into an elastic plastic part and a damage part now. And the elastic plastic part depends on a set of internal hardening variables and so on, and especially also on the damage variable. And as I said, we are dealing with a non-local model. So this damage dependent part is a function of the damage state and also of the gradient of the damage. It's usual in this phase field community, so to say, to apply also some kind of split hypothesis concerning tension and compression states within the material. And that's denoted here within with this plus and minus sign in this upper index. And the most classic approach you might probably find in literature concerning phase field models is to use essentially a quadratic potential, as it's also known from, for example, linear elasticity, a quadratic potential also for this damage dependent part. So it is both quadratic in the damage variable itself, as also in the gradient of the damage variable. And that's coupled with material parameters. So the fracture toughness, or critical fracture toughness, and this length scale parameter that I told. We also need a degradation function So again, a very classical approach is to use a quadratic approach here. And this degrades essentially the stress states within the damaged regions of our model. Now, in terms of the plasticity model, for the deformational part of our model, we will use exactly the material model my colleague previously introduced. So I will not dive that much into here. Although I have to admit, or that's a good point now maybe, to admit that this is very much work in progress. So essentially, we have not yet implemented this model in conjunction with the phase field approach, which is why, for the sake of this part of the lecture, of the talk, I will confine to the classical von Mises hypothesis with kinematic and isotropic hardening only. Nevertheless, in terms of the understanding of how this phase field model is working, we will get exactly the same insights. It's more of a quantitative difference. Now, speaking of, we need to address how the deformational and the phase field part are now coupled. And the coupling is essentially exactly in the evolution equations of the internal variables. So we have, again, the Armstrong-Frederick approach with isotropic and kinematic hardening. And this is extended now by this degradation function. We have, again, the rate of accumulated plastic strain. And also, if we wanted to include the deformational hardening part, this would happen in exactly the same way. As I said, we will also need a continuum damage mechanical approach. And essentially, the commonly used damage evolution equation in this case looks as follows, that damage evolution is always coupled to the evolution of plastic deformation in terms of this rate here. And also, we have a so-called thermodynamical driving force, omega, which is basically very standard in the phase field approach in this manner here. Note that this here is the Laplace operator, so this omega is again a non-local quantity. We have material parameters M and Q, and we have also a function B capturing the influence of the stress state. And in this case, for the sake of this talk here, I want to use a very simple one, incorporating only the so-called stress triaxiality. So essentially, for negative stress triaxialities below -1/3, there will be no damage evolution. Now, coming to the implementation and the numerical evaluation of this model, in the finite element context, the phase field variable essentially is nothing else than an additional degree of freedom. And this whole model is solved within the so-called staggered algorithm. So first we have a pure displacement field problem. Displacement field problem, and we hold the phase field value constant. And in the second step, the displacement is held constant and the pure phase field problem is solved. A very major issue when it comes to the numerical evaluations is actually the numerical effort one has to deal with. So for these simulations here, we chose to stick with the most easiest formulation, so to say, we came up with. So essentially, we will use only linear hardening here and a very simplified geometrical model. Although, again, for the nonlinear part, or if we wanted to include nonlinear hardening, essentially, we get the same results. It's just a quantitative difference. We also make use of plane stress conditions and the set of material parameters for the phase field part. And the load scenarios that we are going to look at is a combination of tensile stress and the shear stress applied here. So this very first example is nice to understand how this whole model is working. So essentially we have blue and red areas. Blue is the intact material state and red is the broken material state. So with actually this whole red area predicts the crack path that's modeled with this model. And for this first example here, we have a pure monotonic tensile load applied. And it is a very nice example to understand maybe a little bit the mechanics within this model. So we have essentially two influences competing here. That is one, the rate of plastic deformation, and second, the thermodynamic driving force for damage evolution. And what's happening here is that usually this thermodynamic driving force is tending to drive the crack along the horizontal axis here. So it's a symmetry axis, by the way. And the plastic deformation tends to drive the crack along some angled path here. So essentially at the beginning, the influence of the driving force is stronger in this case. At some point, the influence of the plastic deformation within this model takes over and a branching of the crack is modeled. Accordingly, if we apply now again tensile stresses, but in a cyclic manner, we will see a completely different picture, because essentially in each or within each cycle, the amount of plastic deformation is now very small. We will never have larger influence of the plastic deformation than of the driving force. So the crack always grows along the horizontal axis. And that's corresponding to the experiments that our colleagues did earlier. The next example I want to talk about is a pure cyclic shear stress applied. And in this case, we can see that in the corresponding experiment, 4 cracks emanated within this specimen, which is also captured with our model. Of course, there are some differences, but generally speaking, we get a similar behavior. And what I want to address here is the influence of this triaxiality function. So what we can see here is the evolution of the triaxiality within one arbitrarily chosen load cycle. And we can see that at the beginning of this load cycle, we have positive triaxiality at the bottom right and top left corner here, and negative at the according other corners. And this video, if I play the video now, we can see that these values of the triaxiality shift exactly the other way around when the negative part of the load cycle is reached. So essentially, we have within one load cycle always 2 cracks only growing, either the top left and the bottom right, or the bottom left and the top right corner. When it comes to non-proportional loading conditions, I would say these preliminary results are not too bad. Our model captures or predicts 4 cracks actually, whereas in the model or the experiment we had 2 cracks only. Of course, an experiment always has also imperfections and so on. But nevertheless, the first parts of the crack parts are captured quite well. And that holds also for the second non-proportional loading path here. So in both cases, we had a combination of tensile and shear stresses. So keeping in mind all the simplifications we had for this model, we are pretty much confident that if we refine exactly those points, that this model will be very much able to capture most of the phenomena seen in these experiments. And with that, I would like to conclude the talk. So we showed both plasticity model for the non-proportional parts and according phase field extension of this model to capture ductile fracture phenomena. We want to especially deal with the non-proportional loading conditions. And for the future work, of course, we need to determine both the parameters for the anisotropic plasticity part and the phase field part, and also to deal more efficiently with higher load cycle numbers. Thank you very much for your attention.